Good afternoon. Today we will be looking at PID control theory lecture 2, where we will be looking at signal characteristics and transient response. So, by the end you will know what are the different parts of an output signal, and what are the different characteristics of a transient response, and finally what is a steady state. So a quick recap of the last lecture. What is a closed loop controller? Well, a closed loop controller is a controller that controls the input to a device by measuring the output. That is a key point with a closed loop controller. It controls the input to the device by measuring the device's output. That's the key point. So for instance, when you type 25 degrees on a thermostat, the air conditioner will try to control the input power to the air conditioner based on measuring the current output temperature of the room. Now it's important to note that when you use a thermostat, it's actually measuring the room temperature, not the heating element temperature. So it's key to know where your sensors are when you do PID. So it tries to get the output to the desired output state, i.e. the controller will try to get the air conditioner to be 25 degrees. And remember, the controller is constantly trying to correct itself forever, until of course the device is turned off. So when you switch off your thermostat or switch off the air conditioner, that's when the device will shut off. Next, we have what is PID. So PID is a type of closed loop controller. PID has three parameters and they are proportional, integral and differential. So what are we doing today? So in this lecture we will be looking at output signals, namely the transient response and the steady state. So what exactly is a transient response? So a transient response is how a system temporarily reacts to a change in input before stabilizing. But what does that really mean? So think of it this way. When you first turn on a device, it doesn't immediately reach its final desired state. For example, if you have a motor and its desired speed is 100 RPM, it won't instantly jump to that speed and stabilize straight away when you switch it on. So let me draw a graph. So that's our speed, that's our time. So imagine you switch your motor on. Now ideally what happens, probably should change a pen. Blue is a good color. So imagine this is your desired set point and it's 100 RPM. So when you first turn on your motor, you think it would go like this, but in reality that never actually happens. That is an ideal response, but ideal is just ideal. It's like a fantasy world. It's like if everything was perfect, but nothing's perfect. Instead, how a motor actually starts up is it will rise up, it will overshoot, and then it will finally oscillate a little bit until finally getting to a stable point. And you can see how there is the desired point, which is 100 RPM, but this point here is not 100 RPM, not 100 RPM. There's actually this gap over there. And also you can see that it doesn't instantaneously turn on. There's a bit of time between when you switch it on and it actually reaching the 100 RPM. And this is what transient response is about. Now different devices will have a different type of transient response. For example, if I have green, so another motor could start up like this. It could be slower, it could have a smaller top bit or an overshoot. It could stabilize faster. That's all based on the nature of your system. So different systems have different types of transient responses. For example, in an electronic circuit, a transient response is based on the resistors, the capacitors and the inductors. However, a mechanical device will have a transient response based on mass, damping, stiffness, etc. So transient response is all based on your system's model. So transient is based on system model. And that's why it's very important to understand your system's model before you can actually make a controller. Okay, so we looked at what is a transient response, but there's many different parts to this transient response. You can see there is this overshoot here, there is this weird oscillation. So what are those different characteristics? They are the characteristics of a transient response. So firstly, we have rise time. We then have overshoot. We have settling time, and then we have noise. Now, noise is just part of transient response because it's a natural occurring, almost unpredictable event. Our first one, let's talk about rise time. What is rise time? So rise time is the time it takes for a signal to go from its starting value, so say when it's off, to its final value, to say when it's on. So let's draw a graph. So this is our motor, this is our speed, this is our time. At time equals 0. So imagine you turn your motor on. So you switch it on. Now the natural response of a motor is it slowly or maybe even rapidly goes up before then finally settling or oscillating and then settling. So the rise time is actually this period here where it takes to get to the desired speed or its ideal speed. So let me just get a blue marker. So say that's our ideal speed, our final speed, our 100 RPM. So the rise time is actually how long it takes to get from the off position all the way to get to the on position here. That is our rise time. Now different devices will have a different rise time, so you can have a motor B. So motor B, imagine the red one was motor A. Now motor B could start up like this. You can see that the rise time is a lot shorter. So it's shorter rise time. Shorter. And one thing you'll find is a shorter rise time naturally tends to cause a larger overshoot. So that is a really important point to consider when you actually control your rise time, because PID controllers can control the rise time. They are capable of altering the rise time of your system. So you can choose to have a shorter or a longer rise time, and typically a shorter rise time means the system turns on very fast, but it will probably overshoot a lot. And vice versa, if you have a long rise time, your system's going to take a long time to turn on, but it won't overshoot as much. I mean, at the end of the day, do you fancy using a fan which takes ages to get to full speed before finally cooling you down? Probably not. But at the same time, you don't want to press the pedal of your car and then it goes all the way to the speed you want, but then it overshoots and then you get a speeding ticket. So yeah, rise time is very important. Alright, here we have overshoot. You may have guessed what overshoot is from the last lecture, but what is overshoot? So overshoot is how much higher the signal goes from its desired value. It's a natural response of the system and something we must be careful of. So I'll draw a graph with two different motor responses. So that's speed and that's time. So our desired speed, red. Our on value, our desired speed. So if you have motor A, you can see motor A has this thing here, this gap between the on value and its maximum value. So it hits this maximum value, and this maximum value minus the desired value is known as the overshoot. Now, as you can see here, this actually has a massive overshoot compared to the next graph I'll draw. Massive overshoot. I can also draw a different motor like this, and you can see it still has an overshoot, but it's a very small overshoot. Now different systems are going to have a different, how massive the overshoot is depending on your different systems. But one thing that's important to notice is that overshoots can actually be very dangerous, because if you have a motor that is going way past the range that it should be hitting, then you could say burn out the motor. Maybe the machine that the motor's in cannot handle that, or for a heater, for example, maybe the heater's getting too hot, and that's just too dangerous. So overshoot is something we must control. PID is capable of controlling overshoot for us. So remember, overshoot must be kept at a safe level, and that is dependent on the specification of your whole device. Another thing to notice is that, as we discussed in the last slide, a shorter rise time tends to cause a larger overshoot, and a longer rise time tends to cause a smaller overshoot. However, PID controllers can actually create a smaller rise time with a smaller overshoot together. So that's why PID controllers are commonly used. They're capable of making a small rise time and a small overshoot. Let's look at settling time. What is settling time? So settling time is how long a system takes to stabilize after a change has occurred. So let's draw this graph. So that's our speed, that's our time, and this is our on value, so our desired on value. So let's draw a motor in blue. So first we've turned on our motor, it goes up and then it overshoots and then it starts to oscillate a little bit or ring, and then it finally reaches a constant value. So this constant value here is the stable point. So constant signal is the stable point. Stable point or a stable signal. So settling time is how long it takes to first turn on your system all the way till it becomes stable. So that is settling time. Now sometimes settling time is actually the time it takes to first hit the desired speed, the on value. So you can see the motor speed crosses that on value all the way until it becomes constant speed. That could also be your settling time, but that depends on scenarios or circumstances. So that's it. All settling time is time to turn it on, or the time till it first touches the desired speed, all the way till it gets to the constant signal. And this oscillation here, you can see, well, I'll draw that in orange. So you can see that when we overshoot, we actually go back down and we go back up. We oscillate for a bit, so that's oscillations. This is called ringing, so that is known as ringing. Ringing again is natural. The frequency, how long ringing goes for, or how long the settling time goes for, that's all dependent on your natural systems model. And PID can happily control all of this for you. So PID can make the ringing shorter or the ringing amplitude shorter, or PID can make the settling time even shorter if you would like. So that is another advantage of using PID. It's able to shorten this settling time. Now, when discussing settling time, we said that settling time finishes when the signal becomes stable. But what actually is a stable signal? So if I draw you a stable signal, this periodic sine wave, you can see that it has the same amplitude and same frequency. So amplitude remains the same, and so does frequency. Frequency same too. Let's see, same too, and that is forever. So at time equals 10 seconds and time equals 100 seconds, our amplitude is exactly the same. Our periodic amplitude is exactly the same. The frequency is exactly the same too. But then what does a non-stable signal look like? So in blue. So if I draw you a signal that's not stable, typically what happens is the amplitude increases. The periodic amplitude is increasing. So you can see the amplitude is going up, 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 and up. And likewise here. That is not stable. Not stable. And the reason it's not stable because the periodic amplitude and the periodic frequency, well, they're changing. They're not constant. So periodic amplitude and frequency are changing. And so it also works the other way around. So if you have a huge signal and it becomes smaller and smaller and smaller, again, that is, the amplitude is changing, and that is not stable. We are only stable when it's a constant amplitude. So that orange is stable, the blue is not stable. Okay, now we discuss noise. What is noise? So noise is anything unwanted, such as jittering, or unpredictable, such as an unpredictable event, random event. So let's draw a graph. So this graph will be speed, and we have time. So for a motor, let's say you've passed the transient stages, so you've done all our overshooting and done whatever it takes, and now you're at consistent speed. Now you might think it's a straight line, but it's actually not. It's like you can never actually get a consistent speed like that does never changes in values. There's always going to be some jittering. There could be friction of the motor, there could be heating, overheating, whatever it is. But in the real world, we never have a consistent, perfectly consistent system. No, not all noise is created equal. So a little bit of jittering, that's no big deal. We can filter out that. But if I clear this, but some types of noise, for example, a completely unpredictable event, that can sometimes be dangerous. So let's draw a heater. So you're trying to heat a room. So temperature and time. So imagine if your room temperature is a nice stable 30 degrees. So 30 degrees. But then imagine it's cold, very, very cold outside. Someone decides to open the door or open the window, and now 30 degrees plummets down to a very low temperature of, say, minus 10 degrees. So yeah, I mean, that's pretty rapid. So 30 degrees, nice toasty room, and then someone opens the door, and now you've plummeted all the way down to minus 10 degrees. How does your heater deal with this condition? So if you have a bad controller or a controller that is incorrectly tuned, what the controller will try and do is it will try and overcompensate. So when you overcompensate, you just shoot right up, and then you create this overshoot. Because remember, our desired temperature is 30 degrees, but it's shot all the way up. So this is really important, because if I open the door and it plummets to minus 10, my heater should not then rise all the way and overshoot to a massively high temperature. And so then say my room ends up at 60 degrees. Well, 60 degrees is not safe. Humans cannot be in a room 60 degrees. It's too hot, you'll overheat, you'll dehydrate, yeah, and it's going to cause harm. So my heater cannot just overcompensate. So the overcompensation is this part where it overshoots. So overcompensate. A bad controller will see that you've plummeted down and then overcompensate by overheating, by putting too much power into the input, and then the output room temperature rises very, very high to say 60 degrees, and then yeah, that's dangerous. So what we need to do instead, we need to be able to control these unpredictable events. Remember, the heater doesn't, or the controller does not predict, oh yeah, he's going to open the door in a few minutes time, let me adjust for it. No, they do not know that. It's a completely unpredictable event. So controllers, like PID controllers, need to learn to be safely tuned so that they are safe given these unpredictable events. So if I draw an orange marker, now a safer heater would do this. You're at 30 degrees, you plummet to minus 10. Now a good PID controller would say, well, actually, I don't want to overheat, but I can just slowly rise to this 30 degrees and then oscillate around there. And that being a safe oscillation, that might be a maximum of, say, 32 degrees. So that is safe. So we need to make sure we tune our PID controller or any controller so that in a given unpredictable event, it's always reacting safely. So it must be safe. And if your device is not safe, then you cause human harm to the machine, harm to the device, the system, anything. So the important point about noise is how your system reacts, how your controller reacts to that noise. So a little bit of jittering, no big deal, you can filter it out. But a completely unpredictable event like someone opening a door, well, you must make sure your heater is tuned in a safe way so that it doesn't cause harm. Okay, finally we've passed through all the transient response characteristics that we are worried about, and we've moved on to steady state error. What is steady state? So if I draw a graph, like I've always been doing this entire lecture, and time, speed and time. So our motor has overshot, is ringed a bit, oscillated, and now it's at this somewhat constant speed. But this part here is our transient response. Remember, it's reacted to a change. We've turned it on, so it was off here, then we turned it on, and now it's shot all the way up there. That's all our transient response. But then after the transient response, this is all our steady state. So steady state is when it's constant. So steady state is typically periodic, somewhat constant. Obviously nothing's truly constant, but maybe some noise, for example. But the point is periodic. So you constantly see the same signal forever unless a new change occurs. So if you looked at what steady state is, but what is a steady state error? What is the actual error of our steady state? So we've passed our transient signal, and now we've got this as our steady state. So remember, the point with steady state is that it's stable. So the amplitude is not, the periodic amplitude is not increasing or decreasing. It's the same, and the frequency is the same. So periodic amplitude and frequency is constant. You can accept a little bit of noise, of course. So then, what is the steady state error? So we determine what steady state error is based on tolerance. So we can set a tolerance as a percentage. So tolerance levels as a percentage of the desired value or the set point desired. So what does that mean? What does that look like? So here, imagine we have our our orange sine wave. We can set two levels here, and we can say if our signal goes above these levels, these tolerance levels, they are our error. So tolerance level, and then that's also a tolerance level. So this tolerance could be 5%, 2% of the desired value, but our desired value would look like that. So that's our 100 RPM. And we can set a tolerance level of 5%, which means if this desired set point over here is 100 RPM, then this level here would be 105 RPM. And here would be 95 RPM. You can set a tolerance level however strict your device needs to. Remember, this is something you are setting, because you are looking at a specification, a system specification, and you say, I cannot accept if my motor goes any faster than 105 RPM and less than 95 RPM. So that means you set a tolerance of 5%. You can also have a 2% RPM, a 2% tolerance, and that would look like 102 RPM to 98 RPM to 120, 98 RPM to 102 RPM. So that's a 2% tolerance. That's a stricter system. The stricter your system, the tighter your tolerances. Some devices can have 0.5% tolerances, but you could make a relaxed system that has maybe a 10% tolerance. That is all up to you. But the steady state error is when the signal goes above that tolerance. So if I draw a green wave and it goes like this, remember it's still stable, and that is part of steady state, but you can see here we have these errors here, and they are the steady state error. So that is what steady state error is, when our signal is going above our tolerance level. So why did I bother teaching you all about transient response and steady state? Well, firstly, all real world systems deal with it. All real world systems deal with transients and steady state. But most importantly, PID can control them, can control all of these problems. And PID can make them desirable and safe. So again, we don't want a massive overshoot, because a massive overshoot can be very unsafe, but we can make a safe system, a safer overshoot. So remember, PID makes them safe, robust, and predictable. And that's why we've learned about transients and steady state, because PID is capable of controlling them so they are more desirable, they are safer, and therefore you've created a more robust system. Okay, summary. We have looked at the different parts of the output signal, which is transient response and steady state. We have looked at the characteristics of a transient response, and then we've looked at what a steady state signal is. Thank you. Our next lecture will be lecture 3. See you next time. Thank you for watching.